Welcome everyone. Today we would like to welcome everyone to our today's talk of Meet the Young Professionals. And I'm extremely glad to have among us Dr. S.M. Shafiul Alam. So as you probably know that Dr. Alam was a chair of the IEEE graduates of the last decade, which later became the IEEE Young Professionals. So I'm extremely proud to have one of my predecessors of this organization who was a chaired and represented the IEEE YP once. So Dr. Alam was a lecturer in the Bangladesh University of Engineering and Technology. He completed his BSc and MSc degree from there. And after that, he moved to US to do his PhD. He completed his PhD from the Kansas State University, and he then worked in the National Renewable Energy Laboratories. And after that, he moved to the Idaho National Laboratory, where he's currently working as a research scientist in the Power and Energy Systems division. So without further ado, I would like to invite Dr. Alam to give his talk on integrating the renewables, some challenges and how to address them. Thank you.
So can everyone hear me?
Yes, ma'am.
Okay. So do you see the presenter view or the slide view?
Presenter view.
Okay, good. Okay, yeah, thank you, Sajid, for introducing me, and I'm really glad to join this meeting. And I think it's a evening in Bangladesh, and here where from I'm presenting it's morning. So good morning as well as good evening to everyone. And again, let me start the presentation about my topic. It's about integrating the renewables, some challenges and how to address them. So before jumping into the presentation, as Sajid mentioned some of my background, I'm just going it a little bit faster. So one thing is I completed my bachelor and master's degree from Bangladesh University of Engineering and Technology. Then I did my PhD from Kansas State University. After that, I was a postdoctoral researcher at the National Renewable Energy Lab, and then I joined the Idaho National Laboratory as a research scientist and currently working there. So before jumping into detail about the presentation, some disclaimer. So I tried to cite all the sources on each slide for any relevant information. And this presentation should not be assumed to be a direct reflection of my current or previous affiliations. So some of the views may not be the same from the institution that I have worked or presented. So what I'm saying today in the presentation, these are all my view or my understanding, and I really appreciate a good conversation so that it can be further enhanced. So let's talk about the renewables. So what do we mean by the renewables? So before jumping to the renewable energy resources, I'm just presenting like a very simple block diagram about like how we get the electricity. So basically, we may have some type of fuel. Say for example, we may have like a diesel generator or maybe a thermal power plant where we're putting in the steam to run the turbine, and then that connect to the generator to convert to electrical energy. And then there is an important part about the grid interconnection, and then it serves the electric load. So if we see this from a conventional generation resources like a thermal power plant or maybe a diesel generator, so what happens that we directly are feeding in maybe a diesel in a diesel generator that run the rotor in the generator and create the electricity. And that can be also true for like a steam power plant or a nuclear power plant. So basically we have a fuel like maybe like a nuclear fuel, which is creating the heat to recreate the steam that runs the turbine, like in the prime mover, and then it runs the generator to create the electricity. Now, say for example, if we look into the renewable like solar energy, so what is happening? So we have a abundant resource in terms of the fuel from the sun, And the prime mover here is the solar irradiance, which is coming into the on Earth, and we use that over the PV panel. So the PV panel is working as the converter to the electrical energy. And what happens that the PV panel interconnect to the grid via DC to AC conversion. So it's more like an asynchronous connection. So there is no rotating part in the PV panel like in a traditional generation. When we talk about using the traditional generation, we may have a rotating mass, so that rotates in a rated speed that matches the grid frequency, which is 50 hertz in Asia or 60 hertz in North America. So another example is maybe the wind energy. So we have the wind as the resource. The wind speed runs the wind turbine, and then it's interconnect to the grid to serve the electric load. And this is also asynchronous because we cannot control the wind speed, so it is not necessarily matching the synchronous frequency at which the electric grid works. And then sometimes we forget there are other renewable energy resource that is very abundant around us, and we consider it's very obvious. Is the hydropower. So in terms of the hydropower, so this is also renewable because the water itself has the natural cycle by through the evaporation and then again precipitation, and the water is coming back to the earth, and that the water flow we are using for running the turbine, and that helps to generate the electricity. One of the key difference of hydropower with solar and wind is in case of hydropower, we have this rotating mass again, and it can rotate in a speed which is synchronous to the grid frequency. So that's the key difference from solar and wind. So great, we have this renewable energy resources. So it's a clean energy resource. These are renewable. We have abundant supply of these resources, and as well as they are good for Earth, for the climate and everything. But of course, there are some issues with this, because one thing we should remember, these are more like the natural phenomena. So when we talk about the natural phenomenon, when we view the natural phenomena from the human perspective, what we see? We see that one of the key challenge that is for the renewables is these are intermittent. Like we do not know when it is going to appear or when it is going to drop out. It's variable, and it's kind of uncertain. And the figure I'm showing here is kind of an example of a monthly variation in wind speed as well as the solar irradiance, and the bottom figure actually showing the variation in the tidal wave generation. So the main message in this figure is that when we talk about these renewable energy resources which are run by the natural phenomena, the main challenge is understanding their behavior. Now, as a human being, how we can do that? Either we can enhance our visibility, so we can track them very accurately in real time, and we can use the exist more advanced data analytics to understand what is going to happen in the future, so we can adjust our other generation profile more accurately. So as I said, that to challenge and address these issues for the renewable energy resources, so let's see how we can address them one by one. So the first one, as I have said, like that is intermittent, variable, and uncertain. So one thing we can do, that we can incorporate like the existing communication architecture to make it more robust and more accessible to the individual generation profile. So for example, the figure I'm showing here, you can consider here, like say you have a residential area, and each home has its own PV panel. So we have this distributed PV generation resources. So the main issue will be for a distribution system operator is like a better understanding or accurate visibility of individual PV generation. Why is this important? As I have said, that this PV generation, so they have the reverse power flow. So they can even inject power back to the grid, which is not the traditional case. So the main issue will be, it will create like a significant voltage fluctuation, especially in the distribution grid, and it can also happen in terms of the frequency fluctuation in a transmission system. So the operator or the utility need to understand or need to have access to a wider visibility of what is happening in terms of this variable generation. So if we want to understand, or if we want to see the better view of the renewable generation, first thing we have to make sure that we have a good communication. And for this, I'm sharing one of the work that we have done previously about creating like a hybrid communication network, where we are leveraging the existing communication technologies to combine all of them together. So we have a cost-effective solution to make a communication path by via which we can collect the data in real time, and then we can use it to predict what is going to happen, what is happening right now, and based on that, the utility can take a necessary action um, um, for like a quality control of the voltage as well as the frequency. Great. So it is bringing a good advantage. It has a better visibility, but there is another issue. The issue is like when we have this wider visibility, that means we are allowing a mass amount of data coming to the operator. So it's like a data explosion. So it's a huge amount of data coming in real time. And there are other issues in terms of the compatibility. By compatibility, I mean that there are some reporting rate of different energy consuming device, as well as the energy meter that we are using. So as an example, if we talk about the smart meter, so if you compare the standard for the smart meter, in my knowledge, like that there is a difference in terms of the reporting rate within the Europe and as well as within the North America. So in North America, what we have seen, the reporting rate for smart meters varies between 5 minutes and 15 minutes. And for the European standard, they have like a high resolution. So say, for example, now if any utility is bringing in two types of technology into their system, so they have to deal with this kind of issue of reporting rate. So from some zone or some cluster of the load, they may get like a high resolution data, and from other part they may get a lower resolution data. But maybe that zone should require high resolution of the data, because maybe there is a cloud moving in, so there is a much intermittency in terms of the solar generation, or maybe there is a high variation in the wind, so the wind generation may be more difficult. The third one is the ownership. By ownership, I mean to say, for example, when we talk about the utility, so does the utility own the communication network? Not necessarily. So if you see the figure for the communication network, so like when we talk about uh, uh, like the wide area network, so it may be a part of the cellular communication. So the utility may have to have an agreement with the existing cellular communication provider to access the data, and they may charge additional money for that. So it can be a cost burden for the utility that, okay, I need the data, but I'm getting a massive explosion of the data, and I may not need all the data, but I'm being charged for using the wide area communication network. So we are trying to solve one problem to get like a better view of the in presence of high penetration of the renewables, but then we have to deal with the issue of data explosion, compatibility, and the ownership. So so one thing we can do to manage the data explosion is like aggregate the data smartly. By aggregating smartly, what I mean is like leverage some of the key property of the renewable energy resources. So as I mentioned previously, that these are more like a natural phenomena. So if I give the same example of like a solar generation. So think about like a residential zone, or maybe a over a distribution feeder. A cloud is moving in. So the cloud is big enough to create the shadow over like a one feeder or maybe one residential area. So the multiple PV panels within the same zone will have the same experience in terms of the generation because of the cloud movement. And if there are multiple clouds, the same thing will happen. So you can see some level of correlation when we talk about this distributed renewable generation. So not everyone will behave very differently. There may be a cluster of behavior, but you can see some similarity in terms of the behavior when we talk about these renewable energy resources. So we can leverage this correlated behavior to smartly compress the data that we are collecting. So in terms of the theoretical perspective, it's called the compression theory. So it will be a little bit clear to those who are from the communications background. So in communications, we try to compress the data using a sampling rate called Nyquist sampling rate. So the idea here is like if we can compress the data in a rate which is at least twice the maximum frequency content of the signal, then we can decompress it and get the actual signal. Great. But compress sensing says that this is not necessary, because if the set of the data we're collecting, if they are correlated in some way, then we can do random sampling, and the random sampling size can be much smaller than the sample size in the Nyquist rate. And then we can look for the sparsest solution, and we can recover the signal. So the main advantage here is that we do not have to, in terms of the device perspective, we don't have to create like a costly device to create this high sampling rate, and then we have to compress and decompress. Rather than we can use the like a low size random sampling, and then we can recover the data pretty easily. And the third advantage is that since we are saying it's like a random sampling, so what happens, like each data point is being encoded encoded by like a smaller set of random numbers. So in some way you are encoding the data, which has some similarity with the code division multiplexers, where we do the pseudo random code to encode the data and then send it. But in case of the CDMA, it actually widen the spectrum, but that won't be the case for the compressive sensing, because the main goal here is to reduce the sample size and reduce the communication overhead. So great, we can aggregate the data smartly. So what is the application for that? So how the utility will be helpful for that? So one of the key application is that utility wants to understand one thing for sure, is what is happening right now. Say they have they are supporting the customer, and they are saying that there's a cloud movement, or there is a variable wind speed. So they get this data using the compressive sensing. So they have to use the data very fast to understand the overall situation of the grid. So as I said previously, in terms of the quality control for the distribution utility in particular, they are more concerned about the voltage quality. So the voltage should not go beyond the specified value. So say for example, it should be in terms of the power unit between 0.95 and 1.05. So it should be within that range. So if the utility has to do any corrective action, so they have to use this data as soon as possible to understand the other profiles in terms of the voltage. So say for example, we collect the data using the compressed sensing. So there is so we reduce the communication overhead, great, and we may have also reduced the ownership issue in a way, because we are not accessing the data directly. So we are resolving the privacy issue. There will be no violation in terms of accessing individual customer information, and we may also able to reduce the energy meter access, or reduce the channel bandwidth we are using from within the wide area communication through this technique. So one of the, as I said, one of the case here that great, we got the compressed data, how to use it. So typically when we talk about one of the cases using the measurement data in a power system is using the measurement data to estimate the state. So in most of the cases, what we do, we may collect like the measurement, like the real and reactive power consumption, real and reactive power flow over the grid, as well as in some cases some of the voltage magnitude and angles. But the main goal is to understand or get the node by node, bus by bus voltage magnitude and angles. So we want to know those values. So those can be considered as like the unknown value that we want to estimate based on the available data. So there is a numerical approach called the Newton-Raphson that can be used to do that. So one way, the traditional way can be that, okay, we collect all the data. So by capital N, I represent the actual size of the data. So we are transmitting the actual set of the data over that hybrid communication network to the utility or the distribution system operator. They are using the Newton-Raphson method, and then they are estimating the state. So think about it. So they have to make sure all the data being transmitted over the communication channel. It's a big amount of data, and they're already paying the communications service provider for that. But if they can do the alternate approach. So if they can apply the compressive sensing, what will happen that it will help to reduce the data set. So by M, I represent the size of the data set after applying the compressive sensing. Great. Then what they can do? So they will send the data in a reduced set, and then within the DSO they can apply two approach. They can apply the sparse solution approach to recover the actual data set and then use the Newton-Raphson to estimate the state, or they can directly apply the compressed data within their state estimation algorithm to get the voltage profile. So you may ask, okay, within the middle path, I'm getting the solution. So why do we care about the third path or the bottom path? Think about it. So you need to have additional computation to recover the actual data set. Yes, in some critical situations, this can be necessary. But if we can apply the third approach of like directly importing the compressed data within the state estimation algorithm, so it will reduce some computational burden of this like the additional step of computation, which is independent from the Newton-Raphson. And it will also help in terms of storing the data by the DSO. So think from the like computer perspective, right? So when we run any computation in a computer, it has the RAM. The RAM access the actual data set. Within the RAM, it processes the data, and then we get the results. So if we want to run the middle path of sparser solutions, so the RAM has to have this additional step of recovering the entire data set of size n and then do the state estimation. But that is not the case in the third part. So the third part, the RAM will have to use only the data set of m size, which is smaller, and it can do the process more efficiently and recover the data. And ultimately, it can store the data within the compressed size. It doesn't have to recover in real time. Maybe in a later approach or for historical data analysis, at that time they can recover the data using the sparse solution. So so what we understood as of now that, okay, we have the data explosion and then we have the ownership issue. So what we can do, we can apply this concept of the compressive sensing to compress the data, to reduce the communication burden, reduce some cost for the utility with the communication service provider, and we can also make it faster in terms of using the data in terms of the state estimation, as an example. Fine. Then one of the issues still persists is like the data compatibility and the ownership. As I have mentioned that for the smart energy meter, in some case, some of the meter reports the data every 5 minutes, some reports in every 10 minutes or 15 minutes. And nowadays, there are other like micro PMU measurements or power quality devices. So they report the data in a much higher rate. So how to resolve that issue? And of course that issue with the ownership. So one thing we can do is apply it's called a red-jig filter. So actually it has two parts. One is the temporal part, which is called the multi-rate and event driven Kalman filter, and the special part is the kriging, which is the spatial interpolation. So let me go over about the Kalman filtering, that what it does. So within the Kalman filter, what happens that the Kalman filter assumes that there is a state space model. So some state is evolving inherently for the system. It collects some measurement and then try to better estimate that what is the current situation. So if you want to compare with the previous slide, that okay, I'm collecting the data, I'm using some mathematics to estimate the state, it has the similarity. But what brings in by the Kalman filter is that it tracks the behavior. So as the state evolves, it tracks the behavior of how what is happening of the system. So I will try to give like a much better example. So think about like a car. You started the engine of the car. The car is in the parking mode. It's not moving. So at that moment, you see the dashboard. Okay, what is the engine temperature? What is the gas level, or what is the interior situation? So from you see through your eyes those measurement, and then you try to estimate. Okay, how many miles I can go given this amount of gas available. Now, if the car is moving, so what will happen? If the car is moving, you can see the speedometer is changing. So that means and what you are doing, you are observing your speedometer, then you are comparing the speed limit on the highway, and then you adjust your speed of the car. So that is happening in a dynamic situation. So here the state of the car is changing over time. It's evolving. That maybe the car is going in over speed. One state it is the going car is going in a near under speed, or it's going in a near in like a rated speed. So something like that is happening with the Kalman filter. So in terms of the multi-rate and event-driven approach, what does it mean? It means that we are leveraging the idea about this compatibility issue from these different smart meter or other devices, those are sending the sample. So how the measurement being collected for this filtering or state estimation, we have a control over that. We can adjust at what rate the sensing device will report the data in terms of the measurement, as well as the sensing device has the freedom to stop sending the data to the Kalman filter, and it can wait if there is a significant event. By significant event, I mean that, say for example, you have a you are monitoring the voltage. Say in Asia, in Bangladesh, we are monitoring the voltage that okay, it's a 230 volt. So you are monitoring the voltage every maybe 5 minutes, 230 volt, 230 volt. Oh, no change. So I'm not going to report to DSO. Fine. So there is no event. But if there is significant change, say you say suddenly the voltage dropped to 210 volt or 200 volt. So if the policy or the grid code says that okay, if the voltage drops from 230 to 210 or 200, it's a significant event, then the meter is bound to report that. So that means there is this event. That event is activating the meter to say, okay, send the data back to the DSO to know that, okay, the voltage dropped significantly. So that is bringing in this event-driven approach. So that's how we are reducing that how many measurements we are collecting. We are capturing the compatibility of different reporting rate of different energy monitoring devices. And another part is the ownership. By ownership, I mean that it may happen that within an area you have all the PV panels or small wind turbines, and those are all like a behind the meter. What is behind the meter? So behind the meter means that say you own an apartment, and in the apartment on the balcony you put a PV panel, and you directly interconnect the PV panel with your home, but your electricity meter or the energy meter is downstairs, so it does not know that you have a PV panel. Now the utility cannot directly understand from the energy meter that okay, how the PV panel is varying until you allow the access. Like you may have the right that, oh, I do not want to share my PV generation data, it's my property, the way I want to use it is mine. Because maybe there is no incentive. Say that the utility may not tell to you, oh, you are using PV generation, I'm going to pay you back maybe to 3 cents per kilowatt hour since you are using the PV panel. If there is no economic incentive, the customer is not bound to report that they have installed the PV panel, so they can maintain their privacy. Now, the headache for the utility is if there is this kind of variable generation in the grid, so somehow they have to understand that from which location, from which particular location it's coming. So how they can do it? So what they can do, they can put some pilot sensors. So if we have the wind generation, they can put like a pilot speedometer. They do not have to put like in every interconnection of the customer, or they don't have to put the irradiance sensor in every customer. What they can do, they can make like a few irradiance sensor or few speed sensors over their territory. Again, they are bringing in the advantage of the correlation, because the natural phenomena, they show some correlated behavior in terms of the wind speed direction, change in the wind speed, as well as the solar irradiance variation due to the intermittency of the cloud movement. So that's how they are bringing in, they can bring in the advantage of the correlation. So what will happen if they have this pilot data, very few sample of them, and they can use it to interpolate as well as extrapolate that what is happening within their entire territory. in terms of the individual generation. Because how can they do that? So they already know the locations of their pilot sensor. They know the location of their customer. So they have those location variable. So they know the relative distance. So based on their pilot data, they can feed a model that, okay, given my pilot data and the variation in distance, I can see how the generations are varying. The renewable generation is varying. So once they have that model, they can use the model for interpolating uh, um, within their observation limit, as well as they can extrapolate that what is happening within the entire territory in terms of the renewable generation. So that's how these things work. So I try to keep it simple. So the framework that we have used is shown here in the block diagram. So it's mainly has been done for the solar irradiance, but it can be again leveraged for the wind generation. The reason I am saying it is, if I remember correctly, like a few months back, I shared an article about some pilot data collected for wind generation for entire Bangladesh. So that technical report and the data, those are publicly available. And so this method that I just mentioned, it can be used to calibrate and tune the wind generation profile for the entire country of Bangladesh. And it can be better used to understand, okay, whether it makes sense to have wind generation here. Is it cost effective? Is it, if the wind generation, if the wind speed is sufficiently high or not? So that can help in a lot way for putting a small wind farm, or even operating or installing wind farm in some of the islands in southern Bangladesh. So as of now, we understood about this the intermittency, the variability, uncertainty. Great. So we agree that, okay, there is this issue with the natural phenomena. Somehow we have to better cope with it. We have to have a better visibility through a good communication network. Then we have the issue with the data explosion. Somehow we have to compress it. Then we have the issue with the data compatibility, and we have the issue of data privacy. So somehow we have to be smart to have some pilot data and extrapolate the information, and that's how we can at least know, okay, how the generation looks like. So now we have some level of visibility of the generation. Great, fine. The another key challenge is the renewable generation is not dispatchable. So there are sometimes people are confused about this term about the dispatchable. What does it mean? So I can bring in the example about like the thermal power plant. So think about like a nuclear power plant. So you have the option to control the graphite rod to increase or decrease the reactivity in the nuclear core. So that will help to reduce or adjust the steam generation. Why do we want to do that? Because if the load changes, definitely the load will change. We are the human being. We cannot just follow the generation profile to adjust our load, right? So we use the electrical load for our demand. So it's our choice. Whenever we want to use it, we want to use it. So the power plant operator or the utility, they have to adjust their generation based on the load demand. That's how things has been working. Now, when we talk about the solar generation or wind generation, we cannot adjust the generation. The best we can do, we can disconnect them. Like if there is a over generation, that the generation from the wind and solar is more than the load demand, we can curtail the generation. Or if the load demand is high, definitely other power plants will jump in to supply that generation. Then what is the problem with the utility? Of course, utility will be happy. That okay, I'm bringing in some of the power plants. But the big headache for the utility is that the utility planned that for today, that this amount of generation will be in the grid from solar and wind and other generation resources. So it's more like it's called I think unit commitment. So they do the unit commitment one day ahead. So they know that tomorrow I will have this megawatt of generation for this megawatt of load throughout the day. And that's how they plan for whole thing. And then during the day of operation, they do the economic dispatch. Now, when they have the solar and wind, if there is a sudden change, say for example, maybe there is a sudden change in this depression in the weather, and the solar generation suddenly drop. Maybe the wind generation also suddenly drop. So that was not in the plan. So how they can do it? So that's the major issue, that we cannot adjust the generation for solar and wind based on the electric load. So that's why it termed as like it cannot be dispatched. So we cannot just rely on it to dispatch it. That okay, I just connected the PV panel, now I'm going to sleep, no worries. So one of the example, the figure that I'm showing here is for the state of California, and this figure is shared by California Independent System Operator. So what you see here is like the year by year variation in the net load. So the net load is like the total load demand minus the generation from the solar and wind. So it's decreasing. When it's decreasing, if you see during the noon, because during the noon time we have most of the time it's like the maximum irradiance during the noon, because the sun is directly over the earth and we have the maximum PV generation. So if you have a very big amount of PV generation, you're subtracting from your actual load demand. That means it will be like an inverse. It will be like more like an U shape, because the solar generation is more like the inverse U shape, that it's go up and reach at peak and then it gradually goes down. Excellent, no problem. So utility will be very happy. Oh, during the noon time, I have a very low demand of load. The main issue happens when we reach the evening. What happens in the evening? So in the evening, typically kids come back from schools. Uh, we come back from our office. Industry are closed down. So all the commercial or the office area, those are all, they have the less electricity demand. No problem. Now we are back to our home, and then suddenly we have increased demand of the load. We switch on the TV, we switch on the lights, the fans, the air conditioner. We switch on, if we have the electric stove, we switch on them. Suddenly there is a huge load demand. Unfortunately, in the evening the sun goes down. That means the utility will see, oh no, I do not have the solar generation, what to do? So if you see here that there is a sharp increase in the load demand while the solar generation is going down. So if you see, if you can visualize the math, that we have the load minus the PV generation. So your load is suddenly going up, the subtracting part is suddenly going down. So the net load is becoming excessively high. Like it becomes like maybe within a 2 or 3 hours. For California, it may be like hundreds of megawatts per hour ramp up. So it becomes really difficult for traditional power plants to ramp that part, that in that speed. So that's why now what is happening, you may see in different reports that people are talking about combined cycle power plant, or natural gas turbine based power plants, because they have like a high ramping capability. Of course, that's a good solution. Just to mention one thing, that so this kind of a figure, it has a similarity with our very familiar domestic animals like a duck. So that's why it's called a duck curve. So you may have seen in some news or some like energy report about the duck curve. So it's called duck curve because it looks similar in some way in the shape in terms of the duck curve. But nowadays, for different generation profile, I have seen that other curves are coming in. You may see like a camel curve or other type of animal shape type of curve is coming in. Things are becoming more complex day by day. So okay, we somehow got the idea that okay, this generation is not dispatchable. We cannot control it. We have to curtail it, or there are no other options. So you may have think that okay, why don't we bring in something to store the energy? Yeah, we can do that. Great, that is a like a good solution. We can bring in the energy storage, and we can store the energy from solar and wind, and then we can use it in later time. Okay, that's a good solution. But which energy storage is good for you? How can you know that? That is a big issue, because different energy storage devices, they have different operating range. So say for example, if we talk about like a flywheel, so the flywheel is like a mechanical rotating device. It's like it has a low power content, but it responds pretty fast. And there is this ultra capacitor. That is also very low power content, but it can respond very fast. It can charge and discharge within the second, as compared to maybe like a lithium-ion battery or flow batteries. And on the extreme hand, we may have a pump storage hydro, where we have like a two reservoir, like a lower reservoir on the ground level, and an upper reservoir on the mountain level, where you store the water through the pump, and then you use the machine as a turbine mode to generate electricity whenever required. But it's a water-based operation. It's pretty slow, and it has a big power rating. So you cannot say, "Oh, I have a PV panel on my patio. I want to install an ultra capacitor." Does that make sense? So you have to look into that from different perspective, like which energy storage is good for you. So it has different power ratings, whether it is good for transmission systems, whether it's good for the distribution systems, whether it is good for the end customer. And then one of the major issue that I see within the US, that there are almost like three interconnected parties that has to be in consensus for this kind of interconnection, not only for the storage but also for the renewable energy resources. It's called the interconnection agreement with the utility, whether the utility will approve this interconnection. Then we have the regulatory constraint, whether this device will have any safety issue to the wildlife or the surrounding area. And then the third is the licensing. Uh, so every interconnection, if it have some issue with the environmental regulation, it has to be approved by the FERC. It's called the Federal Energy Regulatory Commission. So three things are connected here. And the final one is whoever is bringing in the energy storage or the renewable energy resources, they have to think from the cost benefit analysis, that okay, I'm buying this energy storage, I have to pay for the interconnection agreement, whether I'm able to use it in a way that it can help to increase my revenue. So for that revenue or grid service, I will touch back more detail in some later slide. So as of now, we understood that okay, we are trying to somehow deal with the intermittency of the renewables by having a better visibility, or compressing the data, or using the data in a smart way to understand the overall situation, and maybe bringing in the energy storage to reduce the lack of the dispatchability. So from here, I will take a little bit diversion to one of the specific case. So because this is the current project I'm working on. So this is about like a run-of-river hydropower plant. So what is very special about the run-of-river hydropower plant? From the name, you can understand that it has something to do of the flow of the water. So I can bring in the example of the Kaptai hydroelectric power plant. So the Kaptai hydroelectric power plant, it has a dam, and it's getting the water from the Kaptai lake. So you have a man-made lake, which is a reservoir, and you can adjust the wicket gate opening or the dam gate opening to adjust your generation. For run-of-river hydropower plant, what happens? You cannot say that you have actually like a physically a dam. Of course, you will see the dam, but you have to see in terms of okay, what is the potential energy the dam is bringing? Because when we talk about the dam can help to control the reservoir level. So it does not have any headache. Okay, I have to maintain a certain water flow or not. For run-of-river hydropower plant, what is happening is that it's constrained by the dam construction. It cannot have like a big dam. So if you can compare this image with like the Hoover Dam in Arizona Nevada border, so it's nothing as compared that giant civil construction that they have in the Hoover Dam. So what is actually happening here? So it uses like a bulb turbine because it looks like an electric bulb in shape, and it is a low head operation. By head, I means like the height of the water from the ground to the top of the dam. So it's between 1 meter to 20 meter. It's pretty small. So that means when we talk about like a hydropower plant, basically what happens that if we have a big dam, so we are using the potential energy of the water to convert to the water flow, or that is the kinetic energy, and then we use in the turbine, then to the generator to convert to the electrical energy. So we have the potential energy, convert to kinetic energy, and then to the electric energy. If we talk about the runoff river hydropower plant, the potential energy is very small. The major portion is coming from the flow of the water or the speed of the water. So that's the kinetic energy. So the kinetic energy converted to the electrical energy directly. So great. So some key information here, if you see from based on the previous slide about the solar and wind, and as I mentioned of the hydro, so we have the natural cycle for water. Great, this is renewable. What is the disadvantage? It does not have that flexibility because I cannot control or I do not have that option to have like a reservoir level maintenance. It's entirely run by the water flow or the water speed. So definitely it's not dispatchable. So that's the crucial part. So when we talk about solar and wind, things are very visible to us that, oh, we cannot control the cloud, we cannot control the like the wind speed. But this is the particular case for the hydropower industry, that where they also suffer from this kind of situations. They cannot do this. As I have mentioned, they also have the regulatory constraints, and they may have to maintain certain water flow or the dam behavior for a safe fish passage, and the water quality, the oxygen content in the water. So that's how they are constrained. So these are also issue with like a traditional hydropower plant with the reservoir, but in particular we are focusing on the runoff river because it has the most of these constraints, and it has the severe impact on them. And the second motivation for our study with the runoff river hydropower plant is like this chart is based on the US data and what we have seen that around 31% of the US hydropower, it's either runoff river or maybe the water flow through the canal and conduit. So in terms of the total power hydropower generation capacity in US, it means like around 23 gigawatt. So you have a 23 gigawatt of generation capacity you cannot control, and you don't have any flexibility. So that's a big issue. So so what do we want to do here? What we are bringing in terms of the flexibility, as I mentioned earlier about the grid services, that so the utility, the plant operator or the owner, the revenue stream for them is coming from two key resources. One is they get the money for their capacity. So they say, oh, I have a like a 10 MVA hydropower plant. Okay, great. I will the utility will say, okay, I will pay you maybe 40 cents per kilowatt hour for the entire year. That's the capacity price. That's the capacity revenue. But if you see this figure, we have other options for revenue, like the frequency responsive reserve, regulating, contingency, ramping, and of course, I just mentioned about the energy capacity. So when we talk about the economic dispatch or capacity-based revenue, this is maybe hour or day ahead. So we know the term about that utility do the unit commitment. So it asks all the plant owner, okay, how much generation you are going to provide tomorrow? Oh, I'm going to provide 10 megawatt tomorrow. Very good, no problem. So you are on the list. Great. But when the operation starts on the day, then these events may happen: primary frequency response or fast frequency response. Like maybe there is a sudden change in the load behavior, or like the dark curve, maybe during the evening the solar generation is going down, the load demand is going up. So utility may request, hey, this particular plant A, you need to ramp up. So the plant A may demand, okay, I'm ramping up. For the ramping up, I need money. So you have to pay me money. So that's another service. So these are the services. Those are typically used in North America for to provide provided by the plant operator, and they get the money for this kind of services. So from the plant owner perspective, flexibility means that if they are more flexible, they can participate in a wider range of grid service, so they can have better and more revenue. So how we can bring in most of this flexibility for a runoff river hydropower plant, because we have seen that we cannot control the water flow. It's not dispatchable. So as I have mentioned few slides back, okay, we can bring in the energy storage, and maybe that will help to reduce the issue with the dispatchability. So So in particular, what we are looking into for run-of-river hydropower plants, so we are saying that why don't we bring in like a hybrid type of energy storage? The main reason is, if you see here on the on the bullet points above the table, is the two extreme behavior from the battery, say the lithium-ion battery and the ultra capacitor. So the battery is basically like an energy content device. So like it can contain a huge amount of energy, but the rate at which it can deliver the energy, that is limited. So it has a limited power. Ultra capacitor on the upper hand, it has a very high power rating, but the energy content is pretty small. So it can the ultra capacitor can actually like respond pretty quickly, and it can discharge the charge pretty fast or deliver the energy in a much higher rate than the battery. So there are some services in the grid which is very small time scale. Say there is a grid event or frequency instability or voltage instability. So that happens in a sub-second or in a fraction of the AC cycle. So those are so fast. So maybe the ultra capacitor will be a good option to operate there. Battery can do that, great, but you have to remember that if every device have their like the operation constraint. So I can give an example about like a car. Say you have bought a car 10 years old. Why have you bought it? Oh, you want to drive in like in a rural area, very low speed, no issue. You just go to your grocery, your office, coming back to your home. Very simple life, and the car will go do very well, like in terms of the maintenance and operations. Suddenly, you thought, okay, you want to take the car to a racing field. Think about it. You have a 10-year-old a sedan car. You are taking to a car racing. You are competing with the sports car or the convertible. So what happens during the car racing? So they do frequent braking and acceleration. So they have more flexibility, and they can change the mechanical energy very fast as compared to your sedan car. So your car will be more stressed because it does not have that capability of transferring or transferring the thermal power to your wheel through the drivetrain. So drivetrain is not strong enough to handle that kind of uh, exchange of power. So this will reduce the life of your car again. So maybe when you are done your racing, your car may stop forever. It cannot run. So that can also happen. You can compare it for this energy storage as well. That if we have a like a slower response battery, you cannot use it for a faster response requirement, and it will actually reduce the life cycle of the battery. So that is not a good option for utility because or the plant owner, because they may be paying hundreds and thousands of dollars to buy these devices. They have some warranty. The manufacturer may say that, okay, I have a 30 years of warranty, and but it can operate in this range. So if you operate the device in an extreme situation, the warranty will be voided, and you may have to replace the battery earlier than expected, and it will be a huge burden on your investment, and it may cost more than the revenue you may got. So that's why what we are thinking that, okay, let's make a like a decision of combining both together. So maybe we can reduce the required capacity of the battery, and we can also reduce the required capacity of the ultra capacitor. But they can serve the both need. They can serve in different time scales whenever it's needed, and serve the issue of the dispatchability for energy storage and other grid services. So this part is like a conceptual diagram. So we are still working on the technical feasibility and cost benefit analysis. So I just wanted to share one of the test cases that we are working on. It's called the black start. So what is a black start? So black start is another one kind of service that is pretty common whenever there is a blackout. And what we are trying to see is that how the battery and ultra capacitor help in that case. So before jumping into like the application of the black start, let me give you an idea about what is a black start. So whenever there is a blackout, whenever the grid is fall, it may be for any natural disaster, it can be for the wildfire, or maybe any unexpected cyber or physical attack on the transmission systems or the power plant. So entire grid is blacked out, there is no electricity. So what happens in that case? If you guys, whoever from the electrical engineering background, if you remember from your undergraduate courses of electrical machines, so you have seen that we have some synchronous machine in the lab. We start them, we excite them, we make sure that they are operating the rated voltage, and they almost have the rated frequency. Then we connect to the grid, and then we make sure that they are synchronized. So that is one of the key requirement for interconnecting a new, an existing power plant to the grid, right? So that means the main requirement is that your transmission system has to be live at first. So who will do that? So typically, what happens in the black star that within a power grid, the large, like a very big power plant. So if in the context of, if we say about the projected growth of the power industry in Bangladesh, if you think about the ongoing development of the nuclear power plant or the coal power plant, so they will be this kind of bulk energy resource. So they will start at first, they will make sure that they are operating in the 50 hertz frequency, and they will start to re-energize the portion of the transmission grid, so that the rest of the smaller power plant will see that the transmission is energized, so they will see it's 50 hertz, then they will synchronize to the grid. Gradually, once those grids are energized, they will then interconnect with the distribution utility. And finally, when the distribution utility will see that it has the rated voltage, the frequency is running, and it is making sure that there are sufficient generation capacity online, it will start reconnecting the individual electric load. So it's more like left to right approach on the top figure. That's the traditional view of the black star. The bottom figure, that's for the distribution level black star. So what's special about this? So as I have mentioned earlier, that we can see there like a more and more penetration of solar and wind resources, and then we have this hydropower plants like the runoff river. Why don't we use those generation profiles in advance? Why in advance? Because think about it, in the top figure, what is happening, that all of the right hand side, they have to wait until the bulk power plants are energized. So it's like a long waiting time for recovering from the blackout, as well as another term that's called cold load pickup issue. So what happens, like because of the sudden, because as a distribution utility, you cannot just broadcast to customers that, dear customer, do not switch on your air conditioning system and dishwasher at the same time after a blackout. They can do that if they want to. So there may be a sudden surge of electric load demand, and that may create some issue or the transient event, as I have mentioned, in terms of the frequency instability or voltage instability over the entire grid, and the grid may fall off again. So they have to adjust the protection settings for traditional backstart as well. But when we talk about the distribution level backstart, what we can leverage is that, okay, we know that there is a blackout, the transmission system is not live yet, the bulk power plant are just starting to restart. Why don't we use our distribution level resources, say solar and wind, and maybe we have some storage, so they can start reconnecting to the grid, and they can re-energize the distribution level of the grid, and they can just wait whenever there is a interconnection request from the live transmission system, they will reconnect it. The advantage will be for the distribution level black star, that within the distribution territory, we are using our available generation resources in advance, and we have already started to support some of the critical load. Say maybe the law enforcement offices, the traffic signals, the hospitals. So those are the key issues. Because if it's a blackout, definitely it's after some major catastrophic natural event. So these will be the critical load that has to be supported. So this runoff river hydropower plant, it plays a very crucial role in that case. So if you make a Google search for like a runoff river hydropower plant where they are typically located, based on their size and capacity, they are typically located all over like a medium stream river, maybe that is in a suburban area or in a remote community. So in a big downtown, you will not get a runoff river hydropower plant. They don't have that space to make that. So the thing is, because it still have a rotating mass, so it will be easier for the runoff river hydropower plant to play the key role to re-energize the distribution grid. and make sure that the grid has the 50 or 60 hertz frequency, so that rest of the energy resources like the solar and wind, they can interconnect and start supporting the critical loads. So that's the main motivation of using the distribution level black star. And the figure I'm sharing, this is an ongoing project in national grid of United Kingdom. So this is an open source project profile, so you can go for understanding the research and how it can value your ongoing research and other stuff. I'm just sharing the idea about how people are looking into it. So we are trying to do the case study for the city where I live in. So the lab, Idaho National Laboratory, it is located in the city of Idaho Falls. The lab has actually two parts. One is the research and education campus within the city, and there is another part. It's called a site, which has all the nuclear research facilities, and that is like a pretty big size. It's like around 890 square miles. They say it's almost similar to the state of Rhode Island. So let's focus on the Idaho Falls Power. So it's a municipal hydropower utility. So it has three run-of-river hydropower plants, the lower, city, and upper. So the goal is that, okay, these hydropower plants are operated by the Idaho Falls Power, the distribution utility for the city of Idaho Falls. So why don't we leverage this idea of distribution level black start should there is any issue in the interconnection from the transmission systems, so that they can use this resource to re-energize the grid and other resources can come in. So what is the key point here is run-of-river hydropower plants, because it's a low-head operation and it is being operated by the Kaplan turbine, because of its mechanical design in nature, it starts showing some instability when connecting to the local load. So say, for example, if you have a 10 MVA run-of-river hydropower plant, and the ideal will be it should support 10 megawatt of load, right? So say you re-energize the distribution feeder, you identified the, you identified the critical load, so you started to reconnect the critical load. So you connected 1 megawatt, then 2 megawatt, 3 megawatt. So you are stepping up the load. So as you step up the load connection or step up the load demand to the hydropower, there is a transient event. So it will see a frequency, it will see a sudden drop of the frequency, but the rotating mass of the hydropower will try to catch up pretty fast so that the frequency does not drop too below of the protection setting. Otherwise, it will tip off the hydropower from the grid again. Then no meaning of the black start. That's the ideal case. But what actually happens is that as the hydropower plant reaches its capacity, say it's now currently supporting 6 megawatt, and then you said, okay, I'm stepping up to 7 megawatt. That additional 1 megawatt, it may cause a frequency instability as high as that it can trip off the generation again from the grid, from the distribution grid. So I'm talking about the whole part of the black start. The transmission system is not connected yet. So the intuition is that, okay, that's a big issue. Maybe it is coming from the low inertial response of the rotating mass within the run-of-river hydropower plant, because I said it does not have a big potential energy. It's depending upon the kinetic energy from the water flow rate. So why don't we bring in some device which can inject the real power very fast, so that it can support that surge of load for that few moments, that few sub-cycle of the AC system, so that the frequency does not go very below the protection setting. So we are saying that, okay, let's bring a device which can do a very fast injection of the electric power, or very fast charging and discharging. So obviously I'm talking about the ultra capacitor. So what can we do? Say I'm working in a research lab, or maybe you are working in a university lab. So what do you think? That, okay, I have an idea. I want to bring in the ultra capacitor. I want to see whether it can help. Great. So in the lab setting, you may purchase, some way you purchase the ultra capacitor, or you scale up like a small capacitor to behave in that way. But still in the lab, that's the simulation environment. In the lab, we do not have the actual hydropower plant, right? So second option, we can have an agreement with the power plant and say, oh, hey guys, we want to test our ultra capacitor with you. So I think you will agree that the utility or the power plant owner will not agree in that proposal because they're already running. Because we are not going to test our research when there is a blackout event, or we do not want, and we want to test it when the natural like a natural operation is going on. So the utility or the power plant owner operator say, "Oh, I'm already serving the load. Do you want me to cut out the load right now and allow you to connect your ultra capacitor to do the testing?" It's a power plant. It's not a lab facility. I cannot do that. But we want to show them that it can work. So in the lab, what we have to do, we have to create an environment that can mimic the actual plant scenario. So definitely we cannot build a hydropower plant in the lab setting. But in the lab, we can have the hardware. We can have the ultra capacitor. It's a connecting converter, the grid emulator we can bring in. So we have those hardware part. So and what we want to do is we want to make sure that this hardware part is behaving as it should be when we take it to the hydropower plant. So if we want to take to the power plant, so we have to make sure that this is operating properly. So how we can do that? So we have to make sure that we have a simulation environment. So in a computer, so we can create the exact behavior of the power plant that we want to interconnect with. So we have a simulation model of the hydropower plant, and then we have the hardware that we want to connect in the hydropower plant. So we run this simulation in real time with the hardware in the loop. So those who are attending from the like the power system research community, they already know about this stuff about the hardware and the loop simulations and how valuable it is nowadays in terms of the research. Because in terms of the grid scale application, things change significantly. So I remember like we did like a RC circuit, RL circuit pulse response back in our undergraduate. But there, those tiny resistor or capacitors on the breadboard, the response we have seen, that seemed to us, oh, this is the ideal thing. This is typically happens. Yes, I agree. In the grid scale, ultra capacitor or the storage, things happens almost similarly. But you have to think about the energy content of those devices, how to control them, because when you have been doing that experiment in the lab in the undergraduate level, you are not worried about touching that ultra capacitor, sorry, the capacitor or the resistor to have a shock or electric shock. There are no issue with the protection settings. But now we are talking about like actual system which will have the grid scale application. So there is definitely the issue with the protection systems and other stuff, whether things will synchronize all together, the control will work all together. So you have to verify that part before going to the power plant to do that. So you may ask, okay, the power plant could have bought the device by themselves and they could have done it. Why do we care? So that's where the lab comes in, the research comes in, that we as a national lab, we are funded by the US Department of Energy to take the risk to do this kind of research to validate that okay, there is a established or proof of concept from an academic publication that it should work. So we have to verify that it actually works, and then to take it to the plant. Maybe one day they can shut off the power plant, which can be pre-scheduled, and to make sure that it is actually working with the power plant and demonstrate the results. And then we reach out to the industry to show that, hey, you guys already know that theoretically it should work. We verified in the lab setting. We tuned all the controls in the lab setting. Then we took the hardware on a pickup truck or a trailer truck to the power plant. We connected there. We videoed the all scenario that is happening, and we can show, okay, it's actually working. So that's how we approach the industry, so that the research that we are doing in a national lab setting can be transferred to the real world application. So that is the main goal that from my research perspective, my current research perspective, and the national lab perspective. So regarding this work, so this is the current work that is going on. So the slide I have just shown is from the mainly corely for the like the technical perspective, like the technical feasibility. So now we are working on two aspects of bringing in the battery as well to see the cost benefit analysis. As I have mentioned, that there is the trade-off. So you are investing on a energy storage, then you have the operation and maintenance cost, and then you have to think about how much revenue you are getting from the additional grid service, which will it allow you to cross the break-even point or not. And the second one is, of course, the technical feasibility, whether it's is still applicable in a grid scale situation, how much efficiency I'm getting, and also the controllability. Because if we talk about this hybrid system, there may be independent control or coordinated control of different energy storage, and of course, there is control from the actual hydropower plant. So these are my slides for today. I tried to cover some of my previous and current work where I try to see some of the challenges in the renewable energy integration and how they can be solved. So this is how I want to end my presentation. So I would really appreciate any questions or feedback or further discussion. Thank you.
Thank you very much, Dr. Alam. So we have some discussions in the chat box. So I would go sequentially through the chat box, and afterwards you're always welcome to add more questions to the discussion. So
Uh,
first question is from Annalise. So if you, I see that he's in the audience. So if you could unmute yourself and then go ahead and ask the question.
Yeah. So, how do you want me to? So, should I go from all the questions, or um,
Well, I wanted to give the audience members if they're
sure?
available to ask the questions themselves, but
Okay. Great.
I
Okay.
can
Thank
read
you.
out the question if he is not here. So the question is, what are the different techniques of storage in a microgrid?
Mhm.
When do we need to synchronize? When do we need to synchronize it in a grid? Do we synchronize when the grid is connected to a microgrid?
So, when a grid is connected to a microgrid, so one of the thing is, so that means it's already offline. Sorry, it's already online operation. So, what will happen that if we have like converter based resources like the solar and wind, so they may operate in a grid following mode because the microgrid is already connected to the distribution grid. Now if there is a situation of the blackout or like a how to say it, like a offline situation for the microgrid, in that case the inverters may have the option to operate in a grid forming mode. So that's the main difference. Now if the microgrid is completely based on the converter or inverter based resources, so in that case what will happen that the control has to be designed carefully so that these converters are not conflicting with each other to determine the frequency of the grid. So that's the key issue. But if it happens that like the existing microgrids, we see that maybe they already have maybe a small hydropower plant, or they may have like a diesel generation. So what they do that they try to make sure using this diesel generation or the hydropower plant to synchronize the grid at first to make sure that the microgrid has the rated frequency and the rest of the inverter or converter based resources come in and join the grid. So does that answer the question?
Hopefully, I don't see the question asking person. So maybe
Okay.
if he could ask more or clarify more in the chat box, that would be good. Let's move on to the next question, which is from
Yeah.
Mr. Kaiser. So I would like to request him to ask the question himself.
Yeah.
Hi, this is
Um,
Kaisar from
hi.
Dhaka.
Yeah.
My question is on okay. Now I got my answer of my question that I have a
Yeah.
confusion that on-grid inverter always working when the grid is available. So
Yeah.
when you are talking, when you are saying that mm, in case of present in black start generation, the solar rooftop will act as a black start generation. So my confusion is that without any grid, how the inverter will work.
So if you see that, so as I mentioned in the previous answer, that when I showed the slide about the distribution level black start, there are other resources as well. So, for example, the distribution level black start that is being researched by National Grid ESO. So they already defined it's called the anchor generator. So it may be a diesel generator or a hydropower plant or maybe a small capacity thermal power plant. So they are using that one to make sure the grid is synchronized, and so that the limitation you are mentioning for the interconnection of the solar and wind, that can be resolved. So so in this case, like what we are trying to see that, okay, that we already have this small capacity run-of-river hydropower plant. Maybe they are not able to provide the entire load within the distribution systems, but at least they can make sure that the distribution level grid is energized, so that other resources like the solar and wind can jump in through their converter connection. So I agree with your point that there will be issue of just completely energizing based on the solar and wind. So here, this existing resource from the small hydro can play the role of making sure that the grid is having the 50 or 60 hertz frequency, so that the solar and wind can jump in. So does that answer your question?
Yes, no, that is. But no, but I have another question. No,
Yeah.
in continuation to that, no, for country like Bangladesh, we don't have any runway for hydro generation. So
Yeah.
will it be able to know that we can black start from the solar?
That's a good research question. So definitely, so one thing can be, if there is an option to operate the microgrid situation in a DC microgrid, maybe that will be a more feasible option for Bangladesh. So I see more potential for DC microgrid in the islanded areas in southern part of the Bangladesh, because in the mainland there may be issue with interconnection as well. Whether they so if the when they interconnect with the REB or Power Grid Corporation of Bangladesh. So I do not know how the agreement works, but that has to be resolved, at whether they will allow like a DC microgrid or AC microgrid to connect. If it's an AC microgrid, then definitely some issues has to be resolved to make sure that if the solar and wind are not capable of bringing in the grid back in a microgrid operation, uh, how long you are going to wait for that service. But you pointed out like a good research question. So this is still going on. So theoretically, you can do that. Like you can say that you want to you start with the solar and wind. You connect the inverter to the grid. The grid will see like a sine wave, and it will see that it's a 50 hertz operating frequency. That is great. But the issue is when we start connecting the load, because uh, you can get, it's called the fast frequency response, but in literature you will see virtual inertia, synthetic inertia. These terms are being used nowadays to to mimic the behavior of the inertial response from a rotating mass, but that is not the case. So I always try to make it like a fast frequency response from these devices. So if the fast frequency response is sufficient enough to make sure that the grid is not tripping off, because you have to take care about your protection of your devices, the inverter interconnection, the solar and wind interconnection. So they have their own protection settings, so you cannot just readjust their protection settings for black start and again go back. It will be more complicated. So I see the issues from those perspective, like when you want to do the black start entirely in a converter based scenario. If it is a DC microgrid, you do not have that issue, because you are not going to synchronize anything. So, but if it's AC microgrid, you will have these issues. So that's my opinion.
Yeah. Right now in Bangladesh, policy doesn't allow you that solar energy can act as a black
Mhm.
start, because in that net metering policy it is saying that whenever grid fails, your inverter should stop producing power. Should
Yeah,
should
that
that
is
feed the power to the
the same. Yeah, this is, I think, the same case even in the US. So they do not, as of now. solar and wind resources, no, they do not operate as the black start resource. No, they do not operate in that way.
Yeah, thank you for your clarification.
Yeah. I'll be happy to answer any other questions you may have. You may email me or contact with me.
Okay, sure, thank you.
Thank you very much. So the next question is from Shariar Abdullah. So I would like to invite him to ask the question by unmuting himself.
Thank you. My question is for like renewable rich grid. How can we cope with the big industrial load? Like some industrial load, like steel mills, they have a very fluctuating load pattern. Then is it possible to cope with those pattern using the battery storage or other technology?
That's a very good question. I think, as I had mentioned, in terms of the lack of dispatchability, so when you bring in the energy storage, so that will definitely help. So, but the main issue is what type of energy storage you are bringing in. As I have said that, I think I should have mentioned earlier that for typically for the lithium-ion battery, what we see in terms of the storage duration is between 4 to 6 hours, not beyond that. But if we think about like a pump storage hydro or maybe flow battery system, they have a longer storage duration. So this storage can help to arbitrage the energy, and maybe it can help to reduce the fluctuation. So whenever there is fluctuation in the load side, like a big load, like the industrial load, maybe this battery can jump in and support the load. And as I have mentioned in my presentation about the ultra capacitor. So two things. One is the how big is the fluctuation, and how frequent is the fluctuation. Two things. So if it is so you have to decide based on what will be the size of the like a high power or a fast speed energy storage, or like a slow speed energy storage, based on the situation you are dealing with. So it will depend case by case. So first you have to understand that how many fluctuations you want to handle within 1 hour. Okay, and what is the typical range of the fluctuation within 1 hour? So say if we have like a 100 fluctuations per hour as compared to another situation where maybe 5 fluctuations per hour. So maybe the situation A, with more fluctuation, you want to integrate an ultra capacitor as well to support that, to support the battery, to reduce the degradation of the battery, because it will be charging discharging pretty fast. And then another thing is, if it is like maybe 5 fluctuations in one of the scenario, and maybe the fluctuation is not that big, so you may just end up with the battery. You don't have the ultra. You don't have to have the ultra capacitor. So this is I'm just saying from the one solution perspective. Then you come to the issue of like coordination of all the converters. How you are connecting the battery and the ultra capacitor to the grid. Are they independently connected, or they are all together co-located in the same place and there you are connecting? So these are the multiple questions that you need to answer when you want to deal with this kind of situation, like industrial load fluctuation.
Thank you.
Okay.
Thank you very much. So the next question is from Dr. Faiza. So I would like to invite her to unmute and ask the question. Sorry, you're still muted, I think.
Good morning. My question to you is, when you were talking about the state estimation, you followed the Newton-Raphson method. So that is typically we follow for transmission system state estimation. But when we are talking about the distribution system, we face unbalance in the distribution system, and there is three-phase system, especially in US networks. We face this kind of problem, the Y delta, and some of this distribution system are two-phase, some are three-phase. So when you were going for this kind of state estimation for distribution systems, so how can we deal with this complexity in state estimation?
if we talk about the three-phase unbalanced system for the distribution grid, I remember like I worked a little bit on that, but yeah, for that project, so nothing has been published. So if it was published or there's a final result, I could have shared here as well. So we looked into some of the way to distributed state estimation based on the ladder iterative technique, because maybe that may help in some way, because we know that we can use the ladder iterative technique like the forward and backward sweep to do the power flow analysis for the three-phase unbalanced system, because the whole structure of that analysis can be built in like a matrix format in some way or other. But still, I think it's an ongoing research to deal with from that perspective. But since I have not continued and in that direction further, but I wish I could have given you a better answer about how to solve this issue, or how we can do it. But in my opinion, it's still like an open question. I have seen, like in terms of the academic paper or research, that like people are still working to solve this problem to have a better solution. But I always what worries me, like how computationally efficient is this one? How much data is required? So if you recall in the slide, I have shown that I was trying to reduce the data for this estimation. So from the mathematical term, the ideal situation will be an overdetermined system. So you have more measurement as compared to the state variables. I try to do it more like an underdetermined system. So you have fewer measurements to do the state estimation. But when we talk about the three-phase unbalanced system, I think still people are looking into like an overdetermined system. So you have more data to do the state estimation, and that's how they are trying to solve it. But it will be interesting to see that if we can reduce the data requirement as compared to the state volume.
So do you have any idea in that case, like what's our current distribution system are doing the state estimation? Which method do they follow, or do they have any state estimation or not?
I can be wrong, but in my opinion, I'm not aware about like any commercial software they're using. Say, for example, I know about the OpenDSS or SIME or Synergy. So when I looked into them, they do the state estimation, but what I can say about that is that it's more like a black box. How they are doing it, it will be really interesting to know. For the OpenDSS, I think you will be the better person to answer that, how the OpenDSS do that.
Yeah.
So I know that you have been working
yeah.
with OpenDSS.
Yeah, I know about the OpenDSS. So my question is like, in this scenario, like, do the distribution system utilities are they doing the state estimation or not? Do they require the state estimation or not?
I think they do not. They just want to like monitor, especially the voltages, and because most of the distribution utility, they are just interconnected transmission systems. So they just have to make sure that they may report back to the sub transmission systems or the upper level that, okay, I have a load scenario, load is increasing, I need more generation. Maybe that's what they are reporting. They may have few sensors to collect the data in terms of the voltage profile, and in terms of the real-time monitoring, I think they still depend upon this monthly energy reading that they are getting. So they may do the load forecast that, okay, this is the load profile will look like tomorrow based on the historical load demand. But maybe they are not that much into it for the state estimation. But eventually they have to do it in the near future, because if there is this more frequent and wider fluctuation in the voltage, that will be a big issue.
Yeah, so like basically they are doing some kind of voltage regulation, online tap with online tap changing, and capacitor bank control for reactive power control. So but they need so basically that was one of my concern or question, that is there any state estimation for distribution system. And when you are talking about the distributed energy resources, and we know that some of the distributed energy resources are at home and as a PV panel. So if they are there, so in that case, we might need to have some state estimation. Yeah, thank you for your answer.
Yeah.
Thank you very much. So next question is from Mr. Anjan Devnath. So I would like to request to unmute and ask the question.
Hello. Good
Hi,
morning,
Anjan.
everyone. Yeah, good to see you
Morning.
after many years. Yeah.
Yeah.
So,
Good to see your image.
thank you. So, I have a question like, what is the potential of artificial intelligence based controller over the conventional PI controller for controlling the transients and overshoots for the VSC or the DC-DC converter? So, because we have a lot of data, right? So yeah.
Of course, you have a lot of data. So the thing is, when you bring in the neural network or artificial intelligence, definitely they will do similar, even better job in terms of the controlling, right? But the main issue is the reliability. Reliability in terms of the security as well as the level of control from the human side. So it may not be very wise to give the full leverage to the AI to do the control as compared to having the traditional PI controller. Another thing is that because the neural network is a like core data-driven approach, so the network or the model that you are getting, like in terms of the hidden layer, the weight, the biasing, that will change system to system. Excuse me. So that will change from system to system. So maybe for one system you have designed, you ran the situation, you fitted the model with the artificial neural network, and then you deploy it. But is it transferable? Say you develop the ANN based control. Is it transferable to another case? Say you propose the method that, oh, I developed the AI based control for VSC to reduce the issue of overshoot and transient. Great, awesome. We want to buy your system. You sell it. Then you go to another company. So you have to do the whole thing again.
Right.
And they may say, oh, we do not want to share our data. We thought you have the solution already. How will you handle that? So that's why I say that data-driven approach, so when we have like a pure physics-based definition, so we can blend the physics-based approach with the machine learning. That is a good thing. But completely wiping out the physics by the machine learning approach, it's not a good solution. And definitely, for machine learning, I would share that it has a very wide application, especially in the pattern recognition, face recognition, computer vision, and biomedical engineering, definitely. But you have to see that where they are being applied. Maybe there is no concrete physics or model available. That's why they are trying to do that, and that's giving the promising result. But that's my opinion in your case.
Yeah, so we can't we use, as you said, the physics was combining like the PI controller. Yeah. I mean, kind of hybrid type of model, PI with the ANN, or
because say, so for example, you have the coefficients you have to adjust. So maybe you will have like a feedback loop. It will more like an adaptive filter kind of setting. So you can use the loop, and based on you may have a lookup table. So it can adjust. You will give the range for the three coefficients, how they can be adjusted based on the output. Yeah.
Thank you, Alam. Thank you very much.
Thank you, Adam. Nice to talk to you.
Yeah. Thank you.
Thank you very much. There is a couple of questions from Annelies. I'm not sure if he can unmute himself. I will just read out the question. So firstly, he asked why researchers are using IEC or IEEE standards while designing a system. What compatibility is there, and what is its significance of using these standards?
So, so speaking of the standard is like, so everyone is, say, everyone knows a problem. Everyone wants to get a solution, right? And so I can give the analogy of the time. So I can say, oh, whenever I see the sun on my head on top, this is 12 noon. You can say the same thing, right? So now, if we do not have a standard, then what will happen? When I travel to East Coast or West Coast, I have to readjust my clock significantly. Now, of course, we have different time zones here, but if I move from here to maybe 600 mile west or east, I have to adjust my clock based on, I will see, oh, the moon is not on my head, so I have to adjust my clock again. So we bring in standard to reduce the conflict in terms of the interconnection and interoperability. So when you talk about the IEEE, IEC, these standards, and there are other standards as well. So in terms of the business for different solutions, so anyone who is providing this kind of technical solutions or selling a device or controller, they try to match with at least one standard. So what will happen? They know that some of their customer may be following the same standard. So that's why they say, oh, it's IEEE 1547 compliant device. So whoever is buying it, they will know, okay, if I buy a solar panel, which require a converter of IEEE 1547 compliance, so I will buy a converter with IEEE 1547 standard. Now, if someone is saying, oh, I made an inverter, why don't you take it? I can take it, but maybe the PV panel will not work with it, because not only there is a power exchange, there will be control signal exchange, communication exchange through the Modbus communication or DNP communication. So what will be the message type? How they will interact with each other? How frequent the message will be exchanged? Who will do the controlling? So someone has to define that. So you can think about more from um, like having the law or constitution. So the standards serve the similar situation, like they help to bring together all the solutions so that there are no conflicts while they are protecting their intellectual property, but they can solve the problem. Yeah.
Thank you very much. There is another question. So, how will the electric vehicles change the load curve?
This is still like an ongoing research, because for the solar and wind, in particular for the solar, since we have now seen like a significant penetration of solar, and we, because of its natural phenomena, we know how it would look like. For the electric load, the thing is, uh, the load pattern is still like a kind of indecisive, because the load pattern will be location specific, which location you are talking about. If you are talking about like high presence of electric vehicle, maybe in the San Francisco Bay Area, that is one kind of load situation. But if you talk about like a load situation in a rural area where they have all the diesel or gas operated car, no electric vehicles, so they do not have that kind of situation. So it will vary based on the location, as well as the load pattern. So the utility has the chance to control the load pattern in presence of the electric vehicle by adjusting the charging price. So it can say that you are not allowed, if you charge during the peak hour, you have to pay maybe 3 cents per kilowatt hour. If you charge during the off peak hour, you have to pay 0.5 cents per kilowatt hour. So it's more like enforcing the load shift. So because as of now, electric vehicles are still like a more like a consumer rather than supplying as a generator. So those will come into play to define the load curve. And I think it is still like a in ongoing research in my knowledge. But yeah, that's my opinion.
Thank you very much. There is another question from Sharir Abdullah. So, if you could unmute yourself and go ahead and ask the question.
My question is in USA, does the renewable plan report site environmental data to system operator? If it does, what type of data reported to the operator?
I think it will depend upon the interconnection agreement, and it varies. So if you think from the intuition, that definitely they have to report say for example, if we see in terms of the risk that they can bring in, say we see a lot of issue that how the positioning of the wind turbine may impact the bird movement. Maybe they have to report that one. I'm just saying as an example. For the solar panel, maybe they have to report in terms of how much shadowing they're causing. So say, for example, you have a farm, right? And you may need a sufficient amount of sun for your farm for the agriculture. And maybe you decided to put the PV panel there or something like that. This is still in your territory, but maybe you may have to report like how much shadowing the PV panel is causing. That may reduce the growth of your crops. So those actually come into my mind when I try to answer your questions. But in my opinion, so this is sometimes it becomes like a proprietary information, so they do not typically share what information they are sharing. But if you want to look into it, you have to think from like what risk this kind of generation is bringing to the environment. What is the surrounding environment looks like? Maybe that will play the role in terms of the environmental data reporting to the system operator.
But I think, is it needed for like forecasting my generation for renewables, these environmental data, to forecast like pattern, finding out the pattern from the environmental data?
Not necessarily. The solar and wind farm, they can say, we have an agreement, we are doing the generation, we are not going to share any environmental data. So it's up to them. They may have the privacy because they already have the interconnection agreement that we based on our forecast, we have made the unit commitment that tomorrow we will have this amount of generation. So they may not say, they may not want to share the wind speed or irradiance value, something like that. So in some cases they will do, but you have to think from the business perspective that the solar and wind, they may say, okay, I will share these measurements with you. You have to pay me. So the utility, it will be cost burden for the utility. They will say, okay, I am already paying you for your generation. Now I have to pay for the environmental data. Okay, I will not take your data. I have access to the entire territory. I will put a pilot sensor beside your farm. I will collect the data and then I will try to understand what is happening. That can also happen. It's all about the ownership of the data. Who owns the data? Who wants to share it?
Thank you.
All right, thank you very much. So at this point, I would like to invite everyone to please turn on your webcams. We're going to take a group photo with the speaker. And also, I would like to share my screen briefly while you're turning on the webcams. So as you probably know that we present a virtual certificate as a token of appreciation to our speakers. And let me actually share the correct screen. So this is actually a certificate of appreciation presented virtually on behalf of the IEEE Bangladesh section and the IEEE Young Professionals for being a speaker in today's session and answering all the questions nicely. So we thank Dr. Alom for his wonderful talk and the time he shared with us.
Thank you.
Thank you very much. And let's then go ahead and take the photo. So thank you very much. So is there any other questions that or any other comments anyone wants to add before we conclude the session?
Sajid, may I ask one question?
Oh, actually,
I raised my hand.
has
Yeah.
joined us.
Yes.
Oh, no.
Hi, hello. Nice to see you.
Hi, nice. Yeah.
It's
Nice to
been a
talk with
long.
after a long time.
It's been a long known to each other for 17 years. So I saw some of our classmates and our junior colleagues and some of my students here as well. It must be a very
Yeah.
exciting presentation, exciting moment for you. Just one query from your ROR project that you are currently working on. Conventionally, we know that for the hydropower plant, what we see for the dam-based plant. So usually we use that type of plant for load following plant or the peaking power plant, because it can track the load very well, because it can be controlled from the from the dam side. But what about the ROR? Can they really contribute in load following function, or
No, they cannot. So if you see that, so the example I have gained for the distribution level, so they majorly purchase their electricity from the interconnection. So I think the interconnection is with the Rocky Mountain Power, and so that's why they cannot follow the load. So that's one of the reasons that, okay, if they want to follow the load, or if they want to like somehow have a better revenue, because they cannot control the generation. They have say there is a negative pricing situation or low price, they are continuing to generate. They have the high price, they are continuing to generate. So there will be a situation that they are not having sufficient revenue, although they are running the system, because of the low price, because they have a low load demand, maybe from other situations. So that's the like the big picture that I try to share. And from the hardware side, I just shared about the black star thing, that how they can contribute.
Yeah, so from the, I mean, so this ROR can be viewed as a kind of, it's a combination of, from operational point of view, it is non-dispatchable. But from the, stability point of view, this is a synchronous generator. So this is very much,
of course,
I mean, this
this
interesting
is
one.
very important. This is a very, this is, so my, based on like what I have seen throughout this many of years, that if you make a Google search, renewables,
right,
what do you see?
Usually PV and solar and wind. Yes, solar
so
and wind.
we considered hydro for granted. We forgot that part.
We considered that.
Yeah. And when I came to this lab, when I started studying this part, like, it changed my view that, okay, why don't we, what is the issue with the hydro? Why don't we want to do that? Of course, in terms of the adoption to new technology, or in terms of the progressiveness, definitely hydro is not up to that speed, because you have to understand that you are dealing with the water. There are thousands of regulatory issues. They cannot just adopt a new solution.
Yeah, because water is not only for the power generation. Human life, other part of the human life also depends on it. Like if you have a big dam, the rest of the part can be submerged. So these sort of issues are always there. Now, thank you, Alom. I won't, waste much of your time at this point. Thank you for
No, thank
joining.
you. I really appreciate the feedback. Yeah.
Thank you. Thank you, Sajid.
Thank you, Mike.
Thank you very much, Bhaiya. And also, I would like to thank all the participants who came here, my seniors from BUET, or my former students who all come to this Meet the Young Professional series. And actually, these talks are for you guys to come network and understand the latest technologies. And I really feel honored that all of you could come here and join the session. So with this, I would like to thank everyone for coming in our session today, and would like to thank the speaker again, and would like to conclude this session.
Thank you, everyone. Stay safe, stay healthy. Bye.
Thank you. Thank you, Alam.